Hello, Professor Snell here. I had a group come to me to ask about shear walls, and I just thought I'd record my response so that anyone else could hear it who wanted to. This is a group that came to me in class, and we talked about it some there. They've sent me their model, which is great, so we'll look at that in a minute. But I want to start from the beginning. Again, this isn't a structures class. I'm not trying to teach you structures, but it seems like I need to create a little bit of context. Oh, and by the way, I apologize in advance for the drawings. This is, I'm just using a mouse, so it's going to be super clunky, but maybe better than, hopefully, understandable. So let's say we have a, oops, I'm also getting these shortcut keys working here. Let's see if it works. Okay. Let's say we have a building. That's too big. Say we have a building. And we're talking about loading it. And I'm going to put some kind of structure here. Oops. I mean, whatever. Just trying to make it super simple. So if I have gravity loads coming down, the whole idea in statics is that these actions have to have an equal and opposite reaction. So they need to find a way down through the structure, right? Maybe this one goes over here, whatever. Again, we're not trying to be correct here. And then there's going to have to be an equal and opposite reaction at the base. That's what statics means. It's not supposed to move. Now, of course, it moves, but we're saying that this is how we design it so that we can simplify the equations. These are, this simple setup here are called dead loads. It's essentially gravity, the weight of the building. But we also have loads coming from other directions. Let me try to make this consistent. Could be coming both directions. If it's wind, it's going to actually be more at the top than at the bottom. But I mean, the higher up you go, essentially. But the point is that these are live or lateral. Trying to figure out how this works. Anyway, you get the idea, right? And similarly, they have to then have equal and opposite reactions to them. So how do we deal with that in a building? I can't delete that one. There we go. So the idea is that we have, well, okay, how should I put this? We need to talk about shear. And the idea with that building we just had, oh man, this is so many steps, is that if I'm now on the ground here and I have a load coming this way, right? I need to resist it over here because I need it to come down to the ground somehow, and I need to resist it going back the other way. So action, reaction. Problem is, if I, let's say I have this configuration, oops, sorry, I have I could even just put it in my little, I can have little connections down here, but we are in the ground. if I now load this way, there's really nothing resisting. I mean, it's going to what we call rack, right? Like that. Because there's nothing really, the only thing that could resist the load would be here. And so rather than coming down to the ground, it's gonna deform like this. So how do we get this reaction down here to work? Um, well, there's several ways we can do it. We can do that. We can, let's see, if I have the same setup and I put in some cross bracing, and these could actually even be cables, but let's not talk about that way. And so if I now load it this like this, that load is going to come down. This, let's say this is rigid, and I can now resist that down here. So this is going to be in compression and pushing against this point down here, and so the same thing if I came this way, the load goes down, and I can resist it over here. So this is called bracing. Another thing we could do is just make it a solid, right? So if I have, here's my frame, and if I just, like, I could make it a piece of plywood. So I'm just making an infinite number of triangles here because that's called a diaphragm. I could make it out of concrete. And now that load is being distributed in a way that this is the most typical way to conceive of a shear wall, because what's happening now is this wall is acting as a monolithic unit, and it's trying to push this way, and then this connection down here to the ground is resisting that this way, so it's resisting sliding, and that's what shear is. So let's talk about shear for a second. If let's say I have a post going to the ground, and I want to put a railing on it. So it's a column with a railing. So it's going to have a little hole through it, and I'm going to put a bolt here. Going through that hole. The weird thing about this app is I have to stop every time I make a mark, and sometimes I forget. So if we have, gravity's coming down, here's a load, and then somebody puts their hand here, and that's also a load, right? Down here, this post is going to be, the ground is going to resist that load, but now it's the bolt here that's resisting this load, right? Right at this point. That's called shear because this bolt now is there's going to be a force sliding, trying to make that bolt slide against itself. So if I have this guy going down and the post stays where it is, but I'm just cutting it in sections so we see. So here's where the post was, the hole, and here's where it is now because we've loaded it. We've pushed this down. I probably should have made that flush up there so this would have been clearer. Now my bolt is here and here, and it has broken in shear right there. So that's what shear means. And so uh, in a building, shear can be, there's a lot of ways it can occur. Like if we had, let's say, let me just do it this way. Let's say we have a hill. Here's our initial site. We want to put a building in here. So we're going to cut out some of this hill to put our building in. But then that's going to be confusing. Let me try that again. say I have a hill, and it goes like this, and I decide I'm going to put my building here. I'm going to cut this part of the ground out and flip it over to there. Right? So now I've got a flat surface, but this under here is fill, and it may settle over time. And I put my and then I've got, I cut a hole here, and I put my building on top of it. Oh my God, that's so terrible. Sorry. Um, this mouse thing is crazy. Building, building, building. If this does settle here, right? If this were to settle down, then this part of my building is sitting on solid ground, but this part may settle with would settle with the dirt probably. And now I've got a shear force through here, like this. This part of um, this part of the building is stationary. This part's moving down. That's a shear force. Okay. Same thing happens if we have wind. All right, I have no idea why that's doing that. Oh, man. Okay, so if we have our building again, and we have our wind force pushing against one side, let's say, then down here, we need the building to push back. And one way it does it is by its connection to the ground here. So it's like this is basically friction or however we've connected it. It needs to resist this sliding force. The building, we don't want the building to just start moving over this way. And so we need something, a resistance in shear, and so we need a shear wall. That's the whole idea, okay? So how can we do that? Well, there's several different options. And this is complicated in the real world, but we're just talking about concepts here. We can have, let's go back to our frame. And I already mentioned this slightly. I'm not being completely organized here, but this is just ad-libbed. If I have my frame that's going to, rack, I could put some bracing here, or even like that. We call that a brace frame, but that can be a shear wall because now we're resisting this lateral loading, right? So we would call this a braced frame. If I did this as a solid wall, we call that, and this is funny because this is typically, sometimes it's just called a shear wall. Oh, no, let's not do that. Let's call this, and if you guys haven't learned this, triangles are really strong self-supporting shapes, and a diaphragm is basically a panel that's an infinite number of triangles. So a piece of plywood is a diaphragm, definitely a concrete wall is a diaphragm. So another kind of shear wall we would call a diaphragm. Of course, I'm not doing the same color. Is that how you spell diaphragm? And then another option would be what we call a moment frame. And that's just simply where we have our same original rectangle, and we brace, or I'm sorry, brace, we create moment connections so that this 90-degree angle here will not change when it's loaded. In other words, we are not going to get rotation. And so then theoretically, that load's going to come down here and be resisted this way. Or really more like this way. And this is called a moment frame. All three of these can take shear loads. And so in the context of our class, very simply, we just need to decide. And yeah, for some reason, it doesn't delete the last one. Interesting. All right, just go do this. So let's look at these slides that I showed before. And so here are these types of walls: shear wall, brace frame, moment frame. And the point is, then you can use any of these to resist shear loading in your building. We don't need to know exactly the calculations, or we can use rule of thumb. And I'm just going to even tell you that I just want to see conceptually that you get the idea. So I'm not trying to say that I'm going to worry about exactly where you put them, but it should be conceptually clear. So let's talk about that a little bit. So we have this concept of these walls that we're going to put in place. And the basic idea is that we have, let's look at this, for example. This wall, I'll use pink. So we have to consider lateral loads coming from all four directions. Because let's just say we're talking about wind. We have to assume, and you can design things differently based on the wind in a specific location, but you still have to consider lateral loading happens for a lot of reasons. So this wall here, if this were a solid concrete, for example, these two sides of the wall are resisting the shear loads or the lateral forces in this way, so we're great. Also, these walls are they're resisting lateral forces in this way. And since they're connected to this bigger wall, they're somewhat going to resist the lateral forces on the larger wall. But the point is that in this case, for example, we've got a longer facade here. And so we're going to need some other, this is great. We've got shear in both directions at both ends of our form. I'm thinking we need a shear wall in the middle, though, too. Kind of makes sense, right? Because we've got more loading, more surface area, more linear feet on these longer sides. So this isn't just going to work. Now, this might work if we just had it in the middle. In our case, for our simple design right now, we're basically saying these cores are where our stairs are, and so we want to separate them up because we need two. But there's different ways of laying it out. So if this were all solid shear wall for this building, and this building's actually a square, so maybe I'm wrong. I think it's a little longer here. Maybe I'm not. I don't know. But this looks like, let's see. I think this would be plenty of shear wall for this building because we've pretty much covered the whole thing. We've got some punched openings and we've got all shear walls. Here the idea is that we've got shear walls on the outer edges of the shorter span, and then we've got shear walls in the middle. On the longer span, more of them. And probably the way this would really work is we might even have, we'll look at that in a second. So I hope that is somewhat clear, that we're basically saying we're just going to use a sort of our common sense and say, what's the longer side of the building? Let's make sure we've got, we need to have shear resistance or lateral loading resistance on all sides of the building. But if we have a shorter facade, we need less, and we just have to go case by case to see how we're going to deal with it. And then so here's another graphic of the same thing. So this is this would be, I think, we might want to have a wall right to the middle here, which would be, probably would happen. Even if this was a gallery, you might have a wall here that had, a little bump out on two sides, maybe a thickened header up here, and came down. and this is all solid, but you still had basically an open space in there. But then this could be all together a shear wall, right? Um, but then these are all shear walls. So in other words, we've got this, and we're saying this isn't a moment frame out here, I guess maybe. Then we're needing more lateral loading on this long um, side of the building. And here we've broken up the building into four shear walls structurally that can take the lateral loading from this direction. So the basic question that was asked is, how do we determine where to put them? I'm saying use some common sense. We need it on all four sides. If we've got, like, if you, for example, if you're saying, well, I'm going to have my service cores over here on each end, going down, um, then you definitely, I would say, would need something going up through the middle, maybe just one, or a layout like this. But you can do punched openings like this in them so that you have open space. And if you go back and look at my slides, this is what I did in my little samples. I had our cores on the two ends of a large gallery. Now there's a bunch of others. We have to have our offices and things, so there'd be other buildings. I'm not trying to make it this simple. And then a shear wall in the middle, and it goes through both floors. So that has to be consistent, or not. It can be more complicated. Um, and you'll see this all the time in steel structures. So just start looking around for it. So this is this bracing here is a good rule of thumb. To say a quarter of your bays would be braced, maybe, if you were using this method for shear wall or for lateral load resistance on the exterior of your building, and then it would have to also follow through inside too. So then let's look at the model that this group is working on, and see how they dealt with it, and I want to reinforce them what I told them. So here's their design. It's going nicely. Clearly, we've got like a really long, so we've got a lot more. Um, we've got a lot of lateral loading this way, not so much this way. Of course, if we come around, I mean, that's not completely simple because there's more over here, but it's a long, thin building. Um, so what should they do? Well, the first thing they did is they have their cores at the two ends. Great. So we're saying now, based on what we were talking about before, that since this is the thin side of the building, then we've got this wall. Interesting. I can't zoom when I'm drawing. It makes sense, I guess. We have this wall and this wall, both dealing with the wind this way, or the lateral loading. I think that's plenty on this because that's based, that's we could put another one down here, but I don't think we need to in this case. At least I'm going to say that. And now we have shear wall here too on both sides. That's taking the lateral loading this way, but that's not enough for this whole long thing. So what are we going to do? Well, they already have responded to what I said, which is great. And I'm not, so I think their question is maybe, is this enough? But what they did is they came in and they put a shear wall here in the middle, and then above it they did a brace frame. So this is a solid shear or a diaphragm. So was what I was calling it underneath, and a brace on top. Now, would that be enough? I don't know, but I think it shows the concept, so I'm happy with it. So let's just talk about what they did. They came in over here basically, and um, they I don't know, maybe here there's got to be beams coming across there anyway, right? And so then there's going to be a beam here and here, and then they just put a wall sort of in the middle. with these openings on both sides. Right, so this is their, and here's the the beam or whatever the thickness of the wall. So here's their shear wall right here. I'm satisfied with that. I think that for what we've got, if I back out, but of course I can't. It doesn't take the drawing with me. Our cores here that are taking shear in the shorter end, and we're going to have a single shear wall going through here. Oops, whoa. It just seems to randomly change. I don't know. And then what they did is above it, they put a brace frame right here, it looks like to me. And there's also, I mean, I didn't draw this right, but there's also a beam on top of that or a girder. So that is working together with this brace frame, and I think that's fine as a shear wall in this context. So if we go back and look at, not yet, we haven't even looked at it yet. If we go and just look at a top view. By the way, you guys, it'd probably be good to put your models, on your grid, like at the origin, so they're easier to navigate. So here here's their basic shear wall layout. Oh God, unreal, man. This interface. Okay, so we have our 2-axis shear wall. And I'm thinking these. That's why I even said I think these are concrete, even in our steel building, because that's a great way of doing a shear wall. And then on both the top and bottom floor, we have a shear wall basically going right through here. Now, and we've got some other stuff here. These maybe could be shear walls in here. So, I don't know what a structural engineer would actually say, but for this, I'm fine that we're saying shear, and then sort of, this is splitting the lateral forces. And this is true on both sides, right? And then down here. And then for over here, it's just this wall here is going to be enough, or the cores. Anyway, I hope that answers the question. If not, obviously, please ask me more. I'm trying to think if there's anything else I should say about it. Let's see. No, I think that's what I want to say. And let's go back to this again. Just like with the control layers, I want you to go as far as you can with this and do as much as you have time to do. But the main thing I'm looking for is clarity and that all the concepts are there. So I want to see some shear walls that you could argue at least conceptually are taking on the lateral loads of the building because they're arrayed, symmetrically, or there's more of them on the long axis than on the short axis of whatever form we're talking about. I want the control layers in the places that I'm telling you and well labeled, but they don't need to be completely detailed out. Though there's no reason they wouldn't be, because you can look up details and incorporate them through redrawing them and adjusting them. All right, anyway, let me know if there's anything else, and if I didn't answer the question, just come back again.